Hey guys, this is a lesson on graphing quadratics. So we're starting to graph quadratics, but notice that this is not the standard form of a quadratic. We're missing the b term. We're only going to look at the effects of graphing a quadratic when we're manipulating the leading coefficient a, or when we're changing the constant c. Right? A couple of definitions that we have to be aware of. We know what a quadratic function is. We've seen it before. So a quadratic function in standard form looks like this with ax squared plus bx plus c. The parent quadratic function is just that with x squared. The parent quadratic function is going to be what we're comparing all of these quadratic functions to, right? So the parent quadratic function is just the very basic one. All right, a couple of other definitions is concavity. So what does concavity mean? First, this U shape is called a parabola, and that's what the quadratic function is going to resemble, is that U shape. And concavity is the way it opens. If it opens up or if it opens down. So we can see which one's up and which one's down based on where the arrows are pointing. But if you ever forget, just think about if it's smiling, it's up. But if it's frowning, it's down. Okay. Again, we're looking at parabolas, and that's what a quadratic function does. It makes parabolas, and parabolas are just the U shape that the function makes. We've seen down and up. We could see a concave down and a concave up parabola right now. The one on the left, the orange one, is a concave down parabola, whereas the one on the right is a smile, so it's concave up. Other definitions that we have to be aware of is the axis of symmetry. So the axis of symmetry, which we could see it's labeled right here on the red one, that is a vertical line that divides the parabola into two congruent halves. Okay, the vertical line, we're going to have to write an equation for it every single time and label it every single time. So looking at the one on the left, you'll see that the axis of symmetry has an equation of x equals -3. I'm cool with you guys just writing AOS for axis of symmetry when you're labeling it. The one on the right has an axis of symmetry of 2. All right. The next thing we're going to be looking at is the vertex of a parabola. So the vertex is a point. It has an x and y coordinate, and the vertex is going to be the highest point of a concave down parabola or the lowest point of a concave up parabola. So another way of thinking of the vertex is that it's the point on the parabola that intersects with the axis of symmetry. So we could see that on the left-hand side, the vertex is -3, 2, and the one on the right, the vertex is 2, -4. The left is a maximum, the right is a minimum. All right. Let's look at an example of how to start graphing these parabolas. So the steps for graphing. First thing we want to do is identify the axis of symmetry. Then we're going to have to identify what the vertex is. And then almost last is to make a table of values centered around our vertex. The reason we want to center it on a vertex is because that is going to be symmetrical on both sides of the vertex. So we just want to confirm that it is symmetrical. If it's not, something's wrong with the arithmetic. All right. We always want to label our axis of symmetry as well as our vertex when we're graphing, so just be aware of that. Because we're looking, so we're going to start graphing this one, we're looking at parabolas that have no b term, have no middle term. So for right now, the axis of symmetry is always going to be x equals 0 because it doesn't have a middle term. On the next lesson, we'll see when it does have a middle term how that changes. So the axis of symmetry is 0. The vertex, to find the vertex, remember the vertex is the point that is on the axis of symmetry. So we want to plug in that value for the axis of symmetry into the equation to find out what the y coordinate is of the vertex. So for the vertex, plug in x equals 0 because our axis of symmetry is 0. Find out what y is. Y is also 0. So the vertex is the point 0, 0. Label it. Plot it. The last thing is to make a table of values centered around the vertex. So on the left-hand side of the vertex and on the right-hand side of the vertex, we should have the same numbers. So if we're going to plug in 1 and 2, we should have the same numbers for 1 and -1, and for 2 and -2. Plugging in 1, we get 2. Plugging in 2, we get 2 squared times 2, which is 8. Plugging in -1, we get 2 as well. And plugging in -2, we get positive 8 as well. So you can see that it is symmetrical on both sides. So we did everything right. Plot the points. Draw the U-shaped curve. It should not look straight. It should not be a straight V. It should be a U shape, right? And that is our parabola. Next we have to do is identify the domain and range. With parabolas, with quadratic functions, the domain is going to be all real numbers. You can see that there is no restriction on what x values we could plot in. However, the range is going to depend on the concavity of our graph, if it's concave up or down, as well as the vertex. So we could see that the parabola is concave up, meaning it's going to go up to infinity, positive infinity, and it starts at y equals 0. So therefore, the range is all values greater than or equal to 0. Okay, let's look at this one. First thing we want to do is label our axis of symmetry. So AOS is equal to x equals 0. Graph that. Next we want to do is find the vertex. The vertex when x equals 0 is y equals 0. So the coordinates are 0, 0. Label that. Last thing we want to do is create a table of values centered around our vertex. I'm going to make a 3-column one so you can see the work or my thought process is when I'm plugging these numbers in. So whenever you're making a table of values, you not only want to pick numbers that make sense, that are integer values that you can actually plot accurately, but you also want to use your entire graphing space. So with this one, if I plugged in the number 1, you can see that I'd be left with a fraction. Don't want to do that. Can't really graph that accurately. So don't do it. Plot 2, however, you are going to get an integer value. Always pick good numbers. Plugging in 4, we get good numbers. Go on the opposite direction on both sides. We could see that it is going to be symmetrical. Plot those points. Graph the U-shape. Last thing we need to do is identify the domain and range. The domain of this function is all real numbers. The range, because the vertex is at 0, 0 and it's concave down, it's going to be y is less than or equal to 0. Okay, let's look at this one. Graphing it, first thing you do is graph and label the axis of symmetry. Next thing you do is find the vertex. Remember, plug in the axis of symmetry into the equation to find the y-coordinate. This time, the y-coordinate is -5. So therefore, the vertex is 0, -5. Plot that and label. We want to center around our vertex. I put 0, 0. That should be 0, -5. Whoops. You know it's 0, -5. Plug in 1, it's -4. Plug in 2, we get -1. Same thing on the other side, but I plotted 3 next just because I wanted to see what the number was, not within my graphing space, so I don't have to care about 3 and beyond. Plot in those other 2 numbers to make sure it's symmetrical on both sides, and it is. Plot those points, draw the parabola, and we're good. The domain is all real numbers. The range is going to be all y values, because it's concave up and the vertex is at 0, -5, y values that are greater than or equal to -5. All right. Next example is comparing this graph to the parent function. Now, I highlighted the leading coefficient because we've seen this before, the comparisons to the parent functions. We've seen it with exponential functions, we've seen it with linear functions, and now we're again going to see it with quadratic functions. If the absolute, so I'm going to write it out here, if the absolute value of the leading coefficient is less than 1, it's going to be a vertical shrink. If the absolute value of the leading coefficient is greater than 1, it's going to be a vertical stretch. So remember that. It's going to come up all the time, right? So this is going to be a vertical shrink because the absolute value of 1 is, or the absolute value of the leading coefficient is less than 1. And notice the -4 there. That is going to signify a translation. It is a translation down 4 units of the parent function. Okay, and now we're going to graph this. Same procedure. Find the axis of symmetry. It's going to be x equals 0. Find the vertex. The vertex in this case is going to be 0, -4. Draw and label. Make a table of values centered around the vertex. Plot numbers that are on both sides. Pick numbers that make sense. We have a 1/2 there, so I'm going to go up by 2's. All right, and then same thing on the other side. Plot those points, draw the parabola, and we're good. And we've already compared it. We didn't even need to draw the parent function there, but because we know what these numbers signify. The next slide is just putting it all together in one slide so you can see it. Copy it down if you want to. I've already talked about vertical shrink and stretch. We know that when we have a negative coefficient, it's going to be a concave down parabola, which is essentially a reflection of the parent function across the x-axis, right? And then we've seen what happens when you add or subtract a constant. It shifts it up or down. Let's look at this example. So we are going to be comparing these two functions, x squared plus 6. And how do you get to x squared plus 6 to x squared plus 2? The best thing I would do is graph the functions. So graph the first one, just like a makeshift graph, doesn't have to be anything perfect. We know that that graph is going to have a y-intercept of 6. And also that the vertex is going to be at 0, 6. So it's going to look something like this, right? And the second graph is going to have a y-intercept of 2, or the vertex is going to be 0, 2. How do you get from the red to the green? It's going to go down 4 units. So the answer for this one is C. Okay. Let's look at this next one. We have to figure out what the function is that passes through those 2 points. So the best thing you could do is just plug in those points and see what happens, right? That is an x and a y value on both of those points. Let's look at the second point. Plugging in that second point, we will see that C is equal to 3. We're going to use that and the first point to plug in all of those numbers to find out what we don't know. We don't know what A is. So plugging in those numbers, we get that A is equal to 6. From there, Y is equal to 6x squared plus 3. That is our equation. Okay. The last thing we're going to be looking at is a word problem in this section. With the word problems in these sections, they're usually talking about parabolas that are cross sections or intersecting something. So in this case, we're looking at a solar panel, and we're looking at a cross section of the solar panel. And it has this equation y equals 0.09x squared. But the main important thing is it's asking us to use the graph that is given to us here to find the domain and range. The domain is not all real numbers in this case, right? It's not going on forever. It is starting at -5 and ending at -5, or +5 rather. So the domain is going to be all real numbers, including -5 and 5, everything in between. The range, however, kind of eyeball it. We know that it's kind of starting at 0, but the ending is kind of questionable. I'm going to say like 2.1-ish. I'm not sure. We can actually figure out what that is by plugging in the number for the domain. You can see that that's where the highest points are. Plug in the extremities of the domain into the function and see what happens. So plugging in 5, we could see that the result is 2.25. So therefore, we know now that the range is from 0 to 2.25. All right. And that's it. Thanks, guys. Bye.